To the session afternoon for track 5. We're going to start with Graham Dumpleton, the author of Mod WSGI, and the title of his talk is Web Server Bottlenecks and Performance Tuning.
If you do have your laptops open, you want to follow along. The slides are already on SlideShare. Go to that address, just search for my name. Before we talk about web server performance tuning, it's important to step back and look at the bigger picture. Although newbies especially have an obsession with trying to find the fastest web server, reality is that things are more complicated than that. Systems have many moving parts. The actual per-request latency introduced by a web server is very small in relation to other parts of the system. As far as a user is concerned, the main delays they will notice are those resulting from how long it takes to their web browser to render the page returned by their web application. This will be followed up by network delays when talking to the web application and when grabbing down static assets from media servers or content data networks. The time spent in the web application is therefore a small percentage of time as perceived by the user for rendering a web page being served. Any time delays introduced by the web server will be a much smaller percentage again. Steve Sunders summarizes this disparity between front-end time and web application time in what he calls the performance golden rule. This is that 80 to 90% of the end-user response time is spent on the front end. So if you're after an easy win for improving end-user satisfaction with your website, the front end is where you should start. Although the big immediate gains may be won in the front end, the web application still presents a lot of opportunity to further reduce response times through means other than fiddling with the web server. Improvements can be had in the application code, but also databases or back-end services used by the web application. Is running benchmarks on web servers a complete waste of time then? The answer is yes and no. The sort of benchmarks that are usually published on websites to compare web servers usually serve little value. They generally only serve to give newbies a false sense of security over any decision they make as to which web server to use. Worse is that people forever reference them as the gospel truth when they can be far from it. The main reason that typical web server benchmarks are useless is that they test only a single narrow idealized use case. Web servers are implemented using different architectures and different code. You're better off choosing a web server that you believe has the features you require and then use benchmarks to help explore the behavior of that system. Often the documented benchmarks you find are nothing more than a hello world program. The test then consists of running it at maximum request throughput with some arbitrary number of concurrent users. This does not mirror what real traffic a public-facing web server would receive. It certainly doesn't show what causes the server to fail as load increases, just that it will fail. What should you test then? There are many different use cases one could test, and how anyone performs can be dictated by the architecture of the system, how the code was written, and how the system is configured when the test is run. The more interesting tests are those which deliberately go out to trigger specific problems. This is because it is the corner cases that are usually going to cause an issue rather than the typical use case. What sort of factors can come into play and affect performance? These are varied and can arise from the hardware or virtualized system being used. They can derive from the configuration you use for the specific web server, but also can be influenced by how the Python language interpreter itself works. To make it harder, these can all interplay with each other in unexpected ways. Some things can be out of your control altogether, such as the type of web browser and what type of network the traffic between you and the user has to traverse. Very few published benchmarks try to account for these issues in a realistic way. Requirements as dictated by your own web application or how you decided to architect your overall system can also contribute, such as whether you try and use the same server to serve up static assets. To illustrate how some of these different factors can come into play, I will go through a few specific use cases that present issues in practice and where possible relate them to those factors. These include memory usage, use of processes versus threads, impacts of long-running requests, restarting of server processes, and startup costs. A simple place to get started is memory usage. This is always a hot topic of contention with benchmarks. It isn't hard to find people claiming that Apache is a big bloated memory hog. This benchmark in particular is representative of poorly chosen Apache configuration. Of course it's going to use more memory if you configure it to have 1,000 threads. If servers tested aren't set up in a comparable way, you can hardly expect it to be a fair comparison. Actually estimating the overall amount of memory used is not a difficult exercise. It is, after all, a simple formula which takes into consideration the number of processes, the base memory used by the web server, memory for each additional thread, and the application itself. Things get more complicated when one considers per request transient memory, but ignoring that, one can easily visualize what you're dealing with. In short, adding more processes is going to see your memory usage grow quicker than adding more threads to existing processes. Although some of that per process based memory usage is the web server, the majority of it will in the end be your fat Python web application. To blame a web server for using too much memory is a plain silly when your web application could be using up to 50 times as much memory. The issue really is about what configuration you choose to set the web server up with. What usually happens is that people will blindly use whatever the defaults are for a server. For fat Python web applications which use a lot of memory, this can be disastrous. Apache with its pre-fork npm can, for example, dynamically create up to 150 processes. That is potentially 150 copies of your fat Python web application. So of course it will use a lot of memory. Those servers which are generally seen as faring best as far as memory usage are those whose default configurations use only a single process and a single thread. Guess what? If you configure Apache that way, then the amount of memory it uses will not be much different. Granted, it does help to also strip unneeded modules out of Apache that you don't use to really get the best from it though. So don't start things off by using whatever the default processes threads configurations are, especially looking at memory usage. Do so and you can easily get the wrong impression. Also, don't pick arbitrary values when you have no idea whether it is reasonable. At this scale, a configuration with 1,000 threads will not even fit on this chart. It's somewhere out there. How many processes of threads should you use then? The total number of threads across all processes is dictated by the number of overlapping concurrent requests. How much overlap there is depends on response times and throughput. Processes are preferred over threads, but constrained by memory. The optimal number can also be dictated by how many processes are available. Unicorn recommends, for example, using 2 to 4 the number of processes as you have CPU cores. One can get a feel for how many threads you'll need by looking at thread utilization. That is, how much do the requests take up of the potential capacity? In this example, by adding up the green areas representing the requests coming in over time, we have here a thread utilization of about 2. This means that if all requests were serialized, we would need only 2 threads. Requests don't arrive in such an orderly fashion though, so we need more threads to ensure they aren't delayed. Because response times are generally quite short, it is actually surprising how few threads you can get away with. If the number of threads is too low and the response times or throughput grows though, then thread utilization will increase. Eventually what happens then is that requests will start to back up as they wait for available threads and queuing time will increase. This will add to the delays that the end user sees in their total page load time. If we add processes rather than threads, we can delay the onset of such problems. The reason that processes work better is that the Python global interpreter lock effectively serializes execution within distinct threads of a single process. Adding more processes, though, obviously means more memory. This has got nothing to do with the server now, and a choice you make as to which is going to be bound by how much memory you have available. If you are memory constrained, finding the right balance and what you can get away with in order to reduce memory usage is a tricky problem. It is all made harder when you have no idea what is going on inside of your web application. If a web application has a heavy bias towards CPU-bound activity within the process, then you are forced towards the direction of needing more processes. If your web application is making lots of call-outs to back-end services, and so threads are blocked waiting on I/O more of the time than not, you can get away with using more threads because the threads aren't competing as much with each other for use of the CPU within the same process. If you have no idea, though, what your web application is doing, this judgment is going to be a hit and miss affair as far as tuning the process's threads balance. To make such judgments even harder, you also have long-running requests to contend with. These can arise due to issues in your own code or back-end services, but also due to how much data you are moving around and how slow the HTTP clients are. The basic problem here is that a long-running request, because it ties up a thread, will reduce the maximum throughput you could achieve during that period of time. The unpredictability of request times means you need to also ensure you have a good amount of extra capacity in the number of processes threads allocated. Don't provide sufficient headroom, and when a number of long-running requests can coincide, you'll suddenly find thread availability drops, requests can start backlogging, and overall response time as seen by the user will increase. Where your application code or back-end service is slow, you obviously need to work out why. Sometimes issues can come from places you least expect them. For example, and especially with Django, watch out for how long Postgres database connections take. One thing you can consider in this case is a local external connection pooler such as PG Bouncer. If you're using Apache Mod WSGI or Unicorn, stick Nginx in front of it and proxy requests through the WSGI server. This will make your WSGI server perform better as you'll be isolated from slow clients. The threads in the backend will be tied up for less time, meaning lower thread utilization, thus allowing you to handle higher throughput with less resources. You can also offload tasks such as static file serving to Nginx, which is going to do a better job of it anyway. When introducing a front end, do be careful though of the funneling effect, especially if the number of concurrent requests that can be handled reduces at each step. If your web application backlogs, users may give up, but requests are still queued and have to be handled. Your web application wastes time and may have trouble catching up with the backlog. It is perhaps better to set up servers so that requests time out with a 503 before getting to your web application if you can. Worst case scenario here is a complete overload, where the server never really recovers for an extended period or until you can shut down the server. Request timeouts within the web application where supported can help a bit, but only to throw out long-running requests. As already mentioned, you really need to stop the request getting to the web application if there is no longer a point handling them. Options here vary and solutions available to avoid it aren't always great. You might actually think that doing a restart will solve a problem with backlog requests. You have to be careful here as well though. For some servers, the listener socket can be preserved so any backlog there isn't actually cleared. Further, when performing a restart, new processes have to be created and application code loaded again. This can take time and cause more requests to backlog, so choose carefully when you restart. If you've got a problem with overloading, to totally reset, it is better to do a full shutdown and clear the backlog in the whole pipeline. For fat Python web applications with a large startup cost, server configurations which allow for auto-scaling can also compound problems. When under load and you get a further throughput spike, the server can decide to start more processes. This slows the system down temporarily, causes backlog, and if it takes a long time to start processes, the server could decide to start even more processes again, increasing system load again, blowing out memory, and overloading your whole system. To avoid unexpected surprises, you're better off starting up the maximum number of processes you expect to require or can fit in available memory with your web application loaded. Ensure you preload your web application when processes start and not lazily when your first request arrives. Do everything possible to keep the processes in memory at all time, avoiding restarts. Especially don't use options to restart when some maximum request count is reached. Because the suggestion is that you should pre-configure the server to its maximum capacity at the outset, it does limit the vertical scaling you can do, at least within the confines of the same hardware. So next step, therefore, is horizontal scaling. Keep in mind the same issues about preloading. You don't want to bring on new hosts and direct traffic to them, only for the first request sent to it to be delayed while the application loads. No matter how you set your system up, if problems do arise, the only way you're going to start to be able to understand what went wrong when it does all crash in a heap is through monitoring. If you treat your system as a black box, how will you know what is going on inside? One thing for sure is all those benchmarks you may have run to find out what was the fastest web server are not going to help you one bit. Server monitoring tools, although useful, only show the effect of the problem on the overall system. They don't necessarily provide you that insight of what is going on inside of your web application, as they still largely treat your web application and web server like a black box. A deeper level of introspection is required. When we talk about finding out what is happening inside of your Python web application, the options have been limited. Tools such as Django Debug Toolbar or using the Python profiler are only suited to a development environment. Sentry can be used in production to capture errors, but performance problems aren't going to generate nice exceptions for you. The historical lack of good tools for knowing what is going on inside of your Python web application is why I'm loving my current day job. If you hadn't managed to miss it, I am now working at New Relic. New Relic performance monitoring provides the ability to monitor the front end, your web application, and the underlying server. I'm bringing all that goodness now to the world of Python web, and that's why I'm excited about being there. So New Relic gives you that deep introspection required to know what is going on. I'm, of course, also the author of Mod WSGI. Being able to get New Relic working with Python means I've been able to use the reporting it provides to delve quite deeply into the behaviour of Mod WSGI in different situations. The results have been quite revealing. One of the areas it has helped in understanding is the funneling effects when using daemon mode. And I'll admit there is room for improvement with Mod WSGI, and I'll be trying to address some of the issues I've uncovered in Mod WSGI 4. Summing things up, pick a web server and architecture which seems to meet your requirements. Then use benchmarks to evaluate its behaviour. Don't use benchmarks simply to try and compare different systems. Don't trust server defaults. Configure and tune your whole stack based on the results you get from live production monitoring. Try and use Relic for really deep introspection of what is going on in all the parts of your system. So if you are doing Python web application development, do consider giving New Relic a try. If you're not sure, New Relic does provide a free trial period when you can try all the features it has. And at the moment, we're running a special conference extended trial period of 30 days where we'd normally use only 2 weeks. So give that a go. Even when the trial ends, a free light subscription is available, which still provides a lot of useful information. And finally, if you want to work at New Relic, then come talk to us. Right now, we are looking for a Python developer in Portland. So while you think about how cool that might be, we're working with me. I'll work you hard. We'll see. We've got plenty of time for questions.
Do we have any questions? If you have a question, there's a microphone here up front, so if you can please come down.
I hope you're just not on the way out the door.
No, I do have a question. Since it's a theme today, have you had any chance to observe the effect of PyPy on performance in web servers?
No, I haven't. It's something I really want to do because obviously with our New Relic stuff, we want to actually make sure it works on PyPy. It's pure Python, so theoretically it should, but I haven't tried it. It's one of those things I really want to get to. But from all I've heard about it, it should be wonderful when PyPy is to that level of quality where we can trust it for production web apps.
Okay. I ask because I know some people already are doing production WSGI with PyPy, and I was just curious if it's something that you guys have already started looking into.
No, I haven't had a chance.
Okay. Thank you.
Hi, can you talk about any other techniques for instrumenting your web server and application other than New Relic? If, say, I want to get data into something like Graphite or something like that?
Well, my understanding of Graphite is that it's going to graph the data. It's not necessarily it's not necessarily providing you a way.
So I need to get that data somehow.
Yes, you need to get the data somehow, and that's where at the moment there's been that hole in terms of getting data out of web applications, and that's where with New Relic we're doing stuff, obviously. In terms of some general data collection, I don't know if you saw Adam Lowry's talk yesterday. He's doing work on trying to get metrics out of applications as well. And one of the things I've discussed with him is one of the ideas I've had, which is to come up with a PEP for a standard for a data sampler API so that we can define this thing, and people with any sort of application which will want to generate some sort of metrics can write stuff to produce data that can be produced via this sampler API. And the idea then is that sampler API could be registered with New Relic, or someone could provide an adapter to push that data into Graphite or anything else that people want to do. So I'm really keen on sort of trying to come up with that to sort of push this whole area of metrics collection for apps. And there's an open space that Adam's set up for later this afternoon. I can't remember what time, which you may well be interested in coming along to if you're interested in that sort of stuff.
Thanks.
No one else?
You mentioned that preloading your application is pretty critical and front-loading some of that work. I was wondering if you could comment on some techniques, at least with WSGI, to make sure that your application is preloaded correctly and completely.
In mod WSGI, there is, well, there's a directive called WSGI import script, which you can use to say, I want to preload this WSGI script, which could be the WSGI file itself that you're using for your app, and say I want to preload it into this, into embedded mode or daemon process group into this interpreter. And that'll be done when the process starts up. Now, one issue with preloading though is you look at something like Django. If you follow the traditional recipe for setting up the WSGI application, it imports various Django files, but it doesn't import your actual real app code. And so even if you could sort of do fiddles to try and make it force import more, and I've got a blog post which I sort of explain one way of doing that, it still doesn't import all your application code anyway. So it still lazily loads a lot. So you can try, but it's not always effective depending on what the particular web framework does. Does that answer the question?
Yeah, sounds like we're still screwed.
Yes and no. It depends on the framework. But it would be nice if there were better ways provided for applications to somehow allow you control over preloading, so you can sort of get your application hot into memory first before you start whacking requests at it. Otherwise you get that little bit of delays on your startup costs.
In Apache 2.4, they introduced the like a event backend. You have will WSGI work potentially better with that, or do you have some insight on what? It
works with it, provided you use the mod WSGI source code from the repository, because I haven't backported any changes for some changes they made at the last minute. It went from 2.3.16 to 2.4, and they made a change in 2.3.16 which broke the code. And I only found out about it last week, so I was rushing to fix it. Yeah, the performance is interesting. I only looked at the performance first time last week as well. And my box was in a really weird state, so I don't know whether the measurements I was getting from my Apache 2.2 installation, which was the default Apple one, was right or not. But for Hello World, which I detest as a benchmark, it was actually showing twice as much throughput on event NPM in 2.4 than would have been pre-fork NPM on 2.2. That's got me a little excited, but I need to go back and look properly. So it looks promising. Okay, looks like we might be done.